evaluate each of the following integrals. Integral 1 to infinity x over x squared plus 1 to the 3/2 dx. So the first thing we recognize here is that there's an infinity as one of our limits of integration. So that makes this an improper integral, and that means we need to address the infinity right away. So we change the infinity to a b, and then we'll take a limit as b goes to infinity, and then I'll copy everything else. And sadly for us, we need to copy that limit in the front of every one of these integrals until we've actually done the antiderivative. Okay, so thinking about antiderivative, my first inclination is that if I let u equal this stuff inside the parentheses, then the derivative is just 2x, which looks an awful lot like what's up on top. So it feels to me like a u substitution is going to work here. So we'll let u equal x squared plus 1. And therefore, du is 2x dx. And then our technique is to solve this equation for dx. So we get du over 2x. Okay, so that means that our problem is now limit b goes to infinity, integral 1 to b. Okay, so instead of the thing on the bottom, we're now putting u to the 3/2. And then we copy the x, but then instead of the dx, we put what we solved for, which was a du over 2x. And the idea of this u substitution is that the x's all cancel, and we just get this much simpler integral. So this is equal to limit b goes to infinity, integral 1 to b. Okay, so I see a 2 in the bottom. I'm going to pull that outside as a 1/2. And then the u to the 3/2 on the bottom, I'm going to bring that upstairs so that it just is u to a power, no fraction. And now we can use our basic power rule to integrate this thing. Again, copy the limit. 1/2. Okay, add 1 to the power, divide by the new power, and then we don't need to put the integral anymore because we just did the antiderivative, but what we do need to do is put 1 to b. And because we're about to plug things in for those u's, we want to try to make that expression a little bit more user-friendly for us. Limit b goes to infinity. 1/2. Okay, actually, so the 1/2s cancel now. If you're not sure about that, just multiply like the top here by 2 and the bottom here by 2, and then they cancel here and they cancel there. So all we're left with is a -1. So I've got -1 over, and then the u to the -1/2 is really a square root of u in the bottom. So I think that's as good as it's going to get for us. And that's going from 1 to b. All right, so this is the part where we change the u into 1 and into b. But unfortunately, I've actually been lying to you this entire time, because as soon as we went to u, which was right here, I should have changed the 1 and the b, right? Because the 1 and the b are values of x. The original integral is values of x, not of u. So let's undo the lie that I've been telling. Over here, if u is equal to b, and if u is equal to 1, the question is, I've got that wrong. If x is equal to b, and x is equal to 1, the question is, what are the corresponding values of u? So we've got our equation right here. U is x squared plus 1. So that means that we just take, in this case, we take that guy and square it and add 1. So b squared plus 1. And then we take this guy and square it and add 1. So 1 squared plus 1 is 2. Okay, so that's what we should have had down here. There's a 2 on every single one of these things. And then up on top should have said b squared plus 1. And the nice thing about doing it this way is that we don't have to go back and replace the u with x squared plus 1, right? That was another option. Let's change this u back into an x squared plus 1, but we've taken care of that. Okay, no more lies up on the board. So now we get to just plug in. We're writing this limit one last time. And now we're plugging in -1 over square root of b squared plus 1 minus -1 over square root of 2. And the question is, what happens to this thing when b goes to infinity? So if b is really big, then the squared is really big, and adding 1 and it's really big, and the square root of big is still pretty darn big. So this is -1 over something big. And after all is said and done, that just tends to 0. So that means this integral is going to converge because we got something finite here, 0, minus 1 over root 2, so altogether just 1 over root 2, positive 1 over root 2. Converges to positive 1 over root 2. Okay, part B, not an improper integral, just an indefinite integral, but it's a doozy. So I see the top is less complicated than the bottom, right? Like the power up here is 1, and that's a higher power on the bottom. So maybe letting u equal the whole denominator, 1 plus 4x squared. Then the derivative is 8x dx. And I say, oh, hey, this is super because 8x dx is sitting right there, but you don't get to just ignore the 2. And so we actually are going to take this integral and split it into 2 pieces because we see that we can handle the 8x over. So the question is, can we handle the 2 over? So let's split. Integral 2 over 1 plus 4x squared dx minus integral 8x over 1 plus 4x squared dx. If you don't believe that we're allowed to split it in this way, I'll just remind you that this is something like this. If you have a over b plus c over b, that's really a plus c over b, yeah? So all we're doing is taking something that looks like this and splitting it into 2 fractions where each fraction gets the denominator. Each fraction got that 1 plus 4x squared. Okay, so the second integral, I believe we can handle with this u substitution. What about the first integral? All right, the first integral, you can't let u equal the bottom because the derivative of the bottom is 8x, and you don't have any x's sitting on the top near that 2 up on top. So not that u substitution. The bottom doesn't factor, so it's not partial fractions. But the bottom does look an awful lot like our trig sub forms, one of our trig sub forms anyway. And so we are going to let, normally you'd let x equal, let's see, so it's either a sine of theta or a tangent of theta, and this one has the plus, so it's a tangent of theta. But in this case, it's not x. We have to recognize that this first denominator is really 1 plus something squared. That's what's going to make it look like a trig sub. And what's the something that I'm going to square to get 4x squared? Well, it's a 2x. Copy the 2, copy the dx. Okay, so that means, and then there's the other integral, which we'll deal with separately, but let's take this one all the way to its conclusion. So I think that means that instead of letting x equal a tan theta, we're going to let 2x equal a tan theta. But in this case, a is 1. So we're just going to let 2x equal tan theta. And then the derivative of both sides here, 2, and then how do we write this? Is it 2 dx equals secant squared theta d theta? And then I think we need to solve for dx because we're going to substitute that. Secant squared theta over 2 d theta. Okay, so let's start plugging in and see what happens. All right, there's a 2 on top. It's not going anywhere. 1 plus, all right, 2x squared. Okay, so 2x is really the same as, oops, not that one. 2x is really the same as tan theta. And so instead of 2x right here, we're going to put tan theta. But it wasn't just 2x, it was 2x squared, so that tan theta is squared. And then instead of the dx, we need to put something equal to dx right here in this space, and this is equal to dx. So secant squared theta over 2 d theta. Okay, so that looks worse, not any better, but maybe it'll get better. Let's see. All right, so the 2's cancel. Secant squared on top. Okay, 1 plus tan theta squared. Well, the whole point of this trig substitution is to recognize that 1 plus tan theta squared is part of another identity, a Pythagorean identity. And 1 plus tan squared is just secant squared. And then we'll copy the d theta. Remember, the 2's have canceled. And so that does look better because this is really just integrating 1 d theta. And the integral of 1 d theta is, is just theta plus a constant. We're going to put that plus a constant with the other integral, which we haven't even started yet. So I'm just going to leave it off here. And then we don't want to leave our answer with theta. We want to go back to x. So that means we need to solve this equation right here for theta. So this tells me I do inverse tan on both sides. So inverse tan of 2x is equal to theta. And so that's what we're going to put here. Okay, so that integral is done. Let's go back and give some attention to the other integral. So this is the 8x over. And I think we saw here in green that this u substitution was going to be promising. So I think we have to still solve this green bottom equation for dx. dx equals du over 8x. So let's start substituting in the second integral. Okay, copy the 8x. 1 plus 4x squared becomes u. dx becomes du over 8x. And then, miracle of miracles, the 8x's cancel. And we get this very simple integral with u in it. So let's copy this integral one more time. 1 over u du. And that's supposed to be easy one for us. That is ln of u. I'm going to put absolute value. You can just put parentheses around the u. Don't forget our plus c. And then here at the end, we're not allowed to give an answer with u in it. We need to go back to the x's. And in this case, u is equal to 1 plus 4x squared. So that goes right there. And so I think that's our answer. Minus ln 1 plus 4x squared plus c.